So we look at this. That's a PMP. So we want to look at transistor as voltage switch. Transistor can be used as voltage switch, and if you look at what I have here, I said for transistor to work as a switch, it must work in the cut-off region, off position, and the saturation position, on position. So transistor, we have 3 stages for the IV characteristics of transistor. We have the cut-off region, we have the saturation region, and we have the linear region. You know, when we were treating operational amplifier, we look at the operation of operational amplifier at saturation region. When the gain of the operational amplifier is very high, we say that that operational amplifier is saturated. That is, that operational amplifier, it is the on position and it is working at that particular time. Similar thing is applicable to BJT transistor. So we have the cutoff region. The cutoff region is the operation in the off position, and then we have the saturation region. If the transistor is in the saturation region, it means it is working in on position. So we have 2 stages that are very important when it comes to the operation of a transistor as a switch. We have 3 stages in operation of transistor. They are cutoff, saturation, and linear. So 3 stages when you have the IV characteristics of a transistor. There are 3. The first one is cutoff region. After the cutoff region, we have the saturation region. After the saturation region, then we have the linear region. When using transistor as a switch, small base current will give rise to large current at the collector with addition of flywheel diode to drive large current devices. What you are simply saying is that in the case of transistor, for it to work, we need a voltage at the base, and that we need a current at the base, and that current is usually small, and that small current will give us big or large current at the collector region. This is the input of the transistor. This is the base, and we have our output at this place, which will be the collector. So we can have 1 milliamp at this place, and when it's coming out at this place, it can be 100 milliamp. And if you remember what we have as efficiency, under efficiency we have what is called work output over work input. That principle is the same for anything we are looking at as efficiency or gain in physics. So in the case of transistor, the input in this case is IB. IB is our input, and our output in this case will be our IC, because we are feeding in IB, and what will be the result at the collector current, collector terminal. You know, we have base, emitter, and collector, and this is NPN transistor. And when we are doing this connection, there are some calculations we need to do to be able to know what is the value of this resistor for the emitter resistor, what is the value for the base resistor. Like this Arduino now is like, probably it has been programmed or something has been done with the Arduino. The signal we have in the Arduino, it will be fed into the base of this transistor, and this transistor can amplify that small signal for us to have a very big and large current. This is the IB characteristics of transistor. This lower part is the cutoff region. This is the cutoff region, and this upper part, this place, is the saturation region. To this point now, to this point is our saturation region. After this point to this place is the linear region. After this place, linear region. This is our saturation point. That is, it starts to increase from this point until it gets to the maximum, and it is constant. Any increase in voltage is not giving rise to any increase in current. So we say in the cutoff state, both emitter base junction and collector's base junction are reverse bias. That's in the cutoff stage. You know, for our diode, there's what we call like the diode. You need to overcome certain voltage before it can start to conduct. That is like a 0.7 volt and 0.3 volt. Like the depletion region, you need to overcome that depletion region. So in this case, you need to overcome that before this thing starts to conduct. And this is this lower part is our cutoff region. This cutoff region is approximately equals to 0. It is not 0, but it is approximately equals to 0. So if you increase the current, then the voltage will increase, and you get to a point that no matter the level of voltage that you have, the current will no longer increase. So we now get to a linear stage that you will not have any increment in what we are doing. So if you look at what we have on the screen now, this is my transistor, and this is my base resistor, this is my collector resistor, this is my output voltage. If I'm not supplying any voltage to this, then I will not have any output at this place. If I'm supplying certain voltage to this Vin in relationship to this Rin, I will have my VBE, which is the base emitter voltage. Once I'm able to generate this base emitter voltage, then I will be able to have V output, and I will be able to have high IC. And with that, you can design this transistor to be able to work as a switch. If you look at what we have in this case, this is a switch. This is more or less like an ordinary switch, and this transistor will mimic that. So in the cutoff region, it appears as if there is no flow of current. It appears as if the switch is open. But when we supply some voltage to the base, there will be flow of current, and if it is more than the VBE, then we'll be able to have VCE or V out, and then we'll be able to have IC. And with that, if I want to do anything in this neighborhood, I can plug something to this place and I can have voltage. And if I'm removing this voltage at this place, the voltage at this place too will not be there. And I can easily now make an arrangement with this one. Either I put thermistor or I put an LDR in that region. For example, like what we have in this case now. This is my transistor, and this is my collector region, and this is my light emitting diode. This is LDR. This is light dependent resistor. That is, if it is PTV, that is positive coefficient, like a thermistor now, it can be PTV, that is positive temperature coefficient, or NTC, negative temperature coefficient. So in this case, if I shine light on this, the resistance of this LDR will reduce, and because the resistance of this LDR is reducing, it will vary the voltage that will be available to this base. You know, if you do voltage divider, if I say V, and if I want to know what is, the voltage we are interested in now will be the voltage maybe at this point. And this was the voltage that we have at this point. Let's assume that from this place to this place is 10 volts. If it is 10 volts, And if this is 10k, if I put it as 10k, I can now say my VD, that is V for LDR, will now be equals to the RD times VA over RG plus RT, that is R of the potentiometer. So I can easily know what is my voltage. Let's assume that if the light is not shining on this, it will give me 10k. And if the light is shining on it, it will be maybe just 500 ohms. You will know that will vary the voltage across this point. The voltage across this point will not be the same. So there will be a time that the voltage will be high, there is a time that the voltage will be low. So with that, it will switch on this or switch it off. So depending on the voltage that we have at the base, that's what will determine what will happen at this output. And the same thing goes for this thermistor. This thermistor, this has to do with temperature. If it is positive temperature coefficient PTC, it means if you are increasing the temperature, the resistance will be increasing. If it is NTC, negative temperature coefficient, if you are increasing the temperature, the resistance will be decreasing. But what we are interested in is that we want to know what will be my resistance when, if it is PTC or NTC. And when you are able to get that, it will be a function of what will happen. This one is we have relay. This is booster, like alarm system. This is relay. The whole of this assembly, they are together for relay. So when there is enough power at this point, this relay will be energized, so it will close this circuit. And in closing this circuit, there can be flow of current in this circuit, and there will be sound in this place. But if the voltage at this place is low, is not enough or is not sufficient to close this circuit or to energize the coil of this relay, then this booster will not give us anything. Like this small calculation we have in here, I said let's assume that I have V in, I have the voltage at this point as 3.3 volts. The voltage at this junction for it to start working is 0.7 volts. So it will be 0.7 volts minus 3.3, then I will have 2.6. If I have 2.6, it means it is 2.6 that will be available at this place. So I can know what will be my RB, the resistance at this place. So it means 2.26 will now be equals to RB times IB. And in the data sheet, we would have been given IB. IB most of the time for some of these small PMP, it is 1 milliampere. So I'm having 2.6. I'm having 2.6 volts is equal to 1 milliamp, then times RB. So it will now be 2.6 volts over 1 times 10 raised to the power minus 3 is equal to RB. That will give us 2 point. This one will give us 2.6 kilo ohm, and the closest resistor value under the standard scale that is close to this is 2.7 kilo ohm. 2.7 kilo ohm. So this, for me not to damage this transistor, I will need to put 2.7 kilo ohms at this place. 2.7 kilo ohms. So the 2.7 kilo ohms at this base will be able to give me the ideal current at this place. And if the HIV of the transistor, if it is 100 milliampere, I'll be able to have 100 milliampere at this side, which I can be able to use to do some other work, some other useful work. Example of transistors that can be used as switching transistor are 1 NPN2N2904. You can find most often NPN transistor in low side switch circuit. The other one that can be used is PMP2N3906 for high side switch circuit. You need a PMP style VJT. Then when we are looking at power, TIP120, N channel logic level, FQP30N06L. Some of these are useful as switch, maybe as small signal or high current, or we need them in power electronics. All these, they are useful for switching. Then transistor as a switch, in summary, transistor switches can be used to switch and control lamps, relay, or even motors. When we use transistor as a switch, it can be used to control lamps. Lamps uses very high current, but we can use transistor small current to control very big current. Why? Because we are only using that transistor as a switch, and the advantage of it is that it is faster than electromechanical switch, or it is faster than mechanical switch, because this is electronic switch. In a micro of seconds we get response, and that is some of the things that we have in our inverter. Now when NEPA takes light, in a fraction of second it will change or switch to the other part of the circuit. If you have to switch it on physically, there will be a delay, and then it will affect whatever we are doing. When using the bipolar transistor as a switch, they must be either fully off or fully on. When using the bipolar transistor as a switch, they must be either fully off or fully on. What that is simply telling us is that it is either we use it in the cutoff region or we use the transistor in the saturation region. We are not using it in the linear region. Transistors that are fully on are said to be in their saturation region. When transistor is fully on, then we say it is in the saturation region. Transistors that are fully off are said to be in their cutoff region. There may be some little current, but it's approximately equals to 0. When using the transistor as a switch, a small base current controls a much larger collector load current. When you are using transistor as a switch, though the current we are sending into the base is so small, but the effect at the collector is not something that one can overlook. When using transistor to switch inductive loads such as relay and solenoid, a flywheel diode is used. What we are simply saying in that case is this: like At this very point, the diode will be connected to this point. We connect a diode to this point. So that it can protect the circuit. That's why, so that it will not overdraw current from the circuit and damage the transistor. When large current or voltage need to be controlled, diluting transistor can be used. This is like when it is a transistor that has been cascaded. You will not be able to see it physically. There are so many features in a diluting amplifier. We'll look at it in the course of this class as well. So this is when we are using the base voltage, this thermistor, and this is what is setting this base voltage. This resistor is protecting the base, because if there is no resistor at this base, it will damage the transistor. So we will do a calculation like what we did before to be able to know what is the value of the resistor that can be put at the base of the transistor to be able to supply certain value of a collector current. And usually we use 2.7 kilo ohms. Now, depending on your calculator, you need to know what is your input voltage, what is your input current. Then you'll be able to know what are you putting as your base voltage, just like the way we did our calculation the other time. Generally, transistor and electronic device, they have what we call data sheet, and in the data sheet you will have the maybe open circuit current, open circuit voltage, the base emitter voltage, and the base collector voltage. They will give you VCE, collector emitter voltage. They will tell you the operation power. So with that, you can be able to know what you are to design. They will tell us the HFE, which is also beta, to be able to know what are we going to do and how are we going to model our equation. For any transistor, the emitter, collector, and the base current are related by IE is equal to IC plus IB. This is equation 1. The relationship between the collector and the emitter current is also given by IC is equal to ICO plus alpha IE. Substitute equation 1 into 2 and make IC the subject of the formula. We substitute equation 1 into 2. The whole of this, we bring it here. We bring the whole of this. Because IA is equal to IC plus IB. So if we put in there, we have this. And when we have this, our equation will become this if we collect like terms. And we have IC is equal to ICU plus alpha IC plus alpha IB. I'll bring alpha IC to this side, and we have alpha IC minus alpha IC equals to ICO plus alpha IB. So IC will now be equals to alpha over 1 minus alpha IB plus 1 over 1 minus alpha ICO. So this is our IC. Then I say let beta equals to alpha over 1 minus beta. If beta is equal to this, then it means beta plus 1 will be equals to 1 over 1 minus beta. Now if you say, if I have, if beta plus 1 will be equals to alpha over 1 minus alpha, then plus 1 by this. That is, our IE is equal to IC plus IB. Now it's just like the transistor is like this. So I have current flowing in like this, I have current flowing out like this. So this is my IB, this is my IE, this is my IC. So what is coming in, you know, this the current we have in IB is a function of what we have in IC. IB is what we give rise to what we have in IC. So what the Kirchhoff's rule now, whatever I now have in this IE, it will be IB plus IC. You know, the sum of current entering a loop is equal to the sum of current leaving that loop, or the sum of current entering a loop, the sum total is equal to 0. So I can say that, I think you understand that. Then we say relationship between collector and emitter current is also given by IC is equal to ICO plus alpha IA. If I substitute equation 1 into 2, and this is my equation 1, if I bring it in here, I will have this. So if I have this, I can open the bracket. I will have IC is equal to ICO plus alpha IC plus IB. Then I can have IC minus alpha IC is equal to ICO plus alpha IB. I can now make IC the subject of the formula. I will have 1 minus alpha. Then I have alpha here already. So alpha over 1 minus alpha IB plus 1 over alpha minus ICO. I say let beta equals to alpha over 1 minus alpha over 1 minus alpha. Then I can still go further and say beta plus 1 is equal to 1 over 1 minus alpha. And if I say beta plus 1 is equal to, what is my beta? My beta is alpha over 1 minus alpha, then plus 1. So if I find the LCM is 1 minus alpha. 1 minus alpha in this case will give me 1. That is alpha. Then this one is 1. This one will now be plus 1 minus alpha. So plus alpha minus alpha will give me 1. So it means beta plus 1 is equal to 1 over 1 minus alpha, which is what we have it. So what we now want to do is that I will now replace the whole of this. I will replace the whole of this with beta. I will replace the whole of this with beta plus 1. So I can now say my IC is equal to beta into 1 IB plus beta plus 1 into ICO. And note, beta is the HFE. This is the gain of the transistor. This is the current gain of the transistor. And I said note, output over input. Physics, we always use this. When we say efficiency, it is output over input. We talk about magnification. It will be image height over object height. And image is our output, object is our input. So when you are talking about efficiency, magnification, current gain, it will be what we have in the output over what we are putting in. And this is referred to as beta. And you will always see this in the data sheet of any transistor. This is referred to as the DC forward current transfer ratio, or the DC current gain of the transistor. That is, when the transistor is working, or it is forward biased, or it is delivering current, the gain. And this HFE, if you want to design amplifier, you will need this HFA or beta, for you to be able to know what will be the gain of the amplifier that you want to design. A very small change in the value of alpha is reflected as a very large change in the value of beta. If this alpha, we have just a very small value of this alpha, it will give us a very big value in beta. A very small change in the value of alpha is reflected as a very small change in the value of beta. The common emitter characteristics of the transistor of the same type number differ significantly from one device to another. So you cannot say because you know the characteristics of a transistor, you have another transistor, you want to use that same characteristic for it. As a matter of fact, if I have a transistor like this, and if this is emitter, and this is base, and this is collector. If you have another transistor, excuse me. If you have another transistor, this may not be the base, this may be the collector, and this may be the emitter. So you must always look at the data sheet of the transistor to note or to know or to identify what is the parameter of this transistor that I want to use. What is the characteristics of the transistor I want to use? Because any design you want to do, the person who manufactured the transistor, they have done some tests. After the design, they will do some tests on the component to know what is the maximum current that this transistor can withstand, what is the minimum current that can turn it on, what is the maximum voltage, what is the gain of this transistor. After that has been done, they will now mass produce it and they will write those characteristics. And that is one thing that you should be able to be careful about. You must know the characteristics of anything that you are working with. Sometimes when you are working with a material, they ask for the data sheet. From the data sheet, you'll be able to know the function of that particular device or of that particular component. And some of these data sheets, they are available online, and some of them you can buy them. You can buy the hard copy. The value of beta vary considerably. The value of alpha is specified to be 0.98. Some of these things they will give you the data sheet. So when you are holding all those components that we use for our practical or for the experiment, they have data sheet. When you are holding them, they have value that has been assigned to what will determine whatever you want to use them for. So the value of alpha is specified to be 0.98. It's specified to be 0.98 at a particular collector base voltage. So what this is saying is that when I have a voltage at the base at a particular collector base voltage, the value of alpha increases by 0.5% when the collector base voltage is increased. Find the percentage change in the value of beta, comment on the result. What we are simply saying is that I have a particular base voltage and I will have a particular maybe beta, or we have a particular value for my gain. If I change the base voltage, there will be the value that I will have to will change, will not remain the same. So solution A is equal to 0.98. You know, we're told that the value of alpha is specified to be 0.98 at a particular current. So it is 0.98. That is, alpha is equal to 0.98. Recall, let beta equals to alpha over 1 minus alpha. So I will say 0.98 divided by 1 minus 0.98. So this will give me 49. So the gain of this amplifier at this time is 49. If I have 1 amp at my base, when we now have 0.98 into 1 minus 0.98, so is equal to 49. So if I have 1 amp at the other end, it will be giving me something like this. Normally what we have for HFE is something like this. We have it like this: HFE is equal to IC over IB. So for some of the digital multimeter that we have, you can measure your HFE. Once you are able to identify your collector and your base, take the collector, put it in the hole for collector, take the base, put it in the hole for base. If you do that, you get your HFE. If you don't want to do that, get the name of the transistor. Maybe it is 2N42 something. Look for the data sheet of that transistor. You will be able to get what is the HFE of that transistor. So that HFE, it may be 30. It will not have unit because this is in amp and this one too is in amp. So amp will cancel amp. So if it is 30, it means if this one is now 1, it means it will be 1 times 30. This one will be 30. If this one is 40, it will be 40 times 30 for this amp. So any little change in this IB will give us a very large value for this collector current. So new value for alpha increases by 0.5%. So we will now add, that's the question we have here. For the very first one, for 0.98, our value will be 49. That is our beta. It will be 49. Then we were told that we now increase alpha by 0.5%. So if alpha is increased by 0.5%, I will come to this list: 0.98 plus 0.5 times 0.98 divided by 100. Then I add it to what I have here. It will give me 0.985. Look at this. It means I'm increasing alpha by 0.005. 0.005. Ordinarily, I can just add 0.005 to 0.98 to get this. Then, what is now my value of beta? It now be alpha over 1 minus alpha, which you look at the increment, 49 to 66. So, percentage increase, that's 66 minus 49 divided by 49. This is 34.69% by an increase of 0.005. So you can see that this is one of the advantage of a transistor for amplification of current and application of that for it to be used as an amplifier. Then in that question, we were asked to comment on our results. We are asked to comment on our results. From the above results, it is obvious that a small change in the value of alpha will give rise in large change in the value of beta. That is, if there is temperature increment, if there is any small fluctuation to the base current, there will be significant increment in the. Let me load our whiteboard and let me see if you can do this. This is the question. So we should allow you to try more. Oh yeah, tell me your answers. What's your answer now? So you can convert it to micro ohm. Calculation, you will start from IB. When you have gotten IB, you move to IC. When you have gotten IC, you use Kirchhoff's law. That is, IE is equal to IB plus IB. Let's just look at so it said the polarity of the voltage V1 is applied to the input section followed by the emitter base junction. Therefore, the transistor is in active region or in the saturation region. Let's assume that the transistor is in the active region. And if it is in the active region, then it means it is working. Then apply Kirchhoff's voltage law to the input section. V in will be equal to RB times IB minus VBE. And if you are using Kirchhoff's law, all these one will be equals to 0. So with that, I can be able to get what is my VB. And my VB will be equals to, my VB will be equals to IB RB. In the equation, we have been given RB. In our calculation, what we are doing here, we have been able to get what is VB. Because at this very point, I can say V, that's a 5 minus 0.7 will be equals to VB. And with that, I can be able to get what is my IB. If I've been able to get my IB, IC is equal to B I beta plus B plus, and we're told that this ICO is equal to 0. ICO most of the time is approximately equals to 0, because at that time the ICO is approximately equals to 0. Ordinarily, when you get to this level, this point, and you want to calculate, it is just when you say beta is equal to IC over IB. And if you look at it, IC over IB will give us beta, or which is equal to HFE. So in this place, I can get what is my IC. So my IC is 2.51 milliampere. If I now apply Kirchhoff's law, sometimes you can be asked to calculate what is your VCE. And if you look at this equation, this place is 8 volts. So it means this place, I will have certain voltage will be dropped in this point, and I will have some voltage drop at this point. What you are simply saying is that this is my VC resistor. You didn't calculate this. So it will be 8 minus 2 times 10 raised to the power 3, then times 2 times 10 raised to the power minus 3, then minus VCE, it will give me 0. If you evaluate this, then we will have VCE to be equals to 3.7. This should be 2 kilo ohms. This should be 2 kilo ohms. That's 2 kilo ohms. That's what we have here, 2 kilo ohms. Then times this. Then by the time you subtract it, we know what is our VCE. Then VCE is equal to VCB plus VBE. So VCB will now be equal to 3.7 minus 0.7, which is equal to 3.33 volts. Then for the NPN transistor, I can be able to calculate what is my IA. My IA, if we use Kirchhoff's law, it will be IC plus IB.
Thank you and God bless. We appreciate your comments, your feedback as we grow this channel together. Please like, share and subscribe to this channel for more updates, for more information of how you can immigrate to Canada by yourself and without an immigration lawyer or without a consultant. And if you choose to hire a consultant, we'll show you what to do and how to do it, either as a student or as an economic immigrant, or maybe you want to start your own business. Thank you for your time.